Hey, thanks for coming out. I appreciate folks turning out on a day like this. I mean, even in the rain, there's lots of stuff you can do outside still. Plus, there's no rain anymore. And I see a lot of thumbs up. Is that just volume or content? I see a number of familiar or semi-familiar faces in the crowd. I'm sure you have something to contribute to the topic. And what I was going to try and do is finish by maybe about 7:45 or so that we have time for questions and discussion. Just so I get a better feel, I mean, do we have any out-of-towners here? I mean, or is this a pure Fairbanks crowd? Welcome. Oh, actually, quite a few. Hey, that's good. Good to see folks from outside of town. So if you, I will try to focus on Alaska issues, but I'd be happy to, go in more depth on aspects of the talk that may not be as familiar to you. But I do know that there's a bunch of people in the audience here who could probably give half of this talk better than I can. So we'll see what they'll come up with during the discussion. So as Althea mentioned, I'm currently serving as director of the International Arctic Research Center, and we've got a great group of people working with us. I'll be drawing a lot on work by several of my colleagues at IARC, as we call it for short, International Arctic Research Center. And I just want to acknowledge that a lot of what I'm showing today isn't necessarily my own work. It's more things that I'm somewhat familiar with, interpreted through the lens of responding to Arctic change. But I encourage you to either come and visit. We're just down the road. We have a great lobby. There's actually nice places to hang out even. We're always happy to entertain visitors, and you might actually then be able to learn more from some of the people who work there. I also want to point you to the IARC website here, or maybe on this side, it's better to see. So a lot of the information products that we generate, you can access through our website. And in fact, now that I mention this, I realize I actually had brought a bunch of flyers that I've forgotten. So I'll have to, if you're interested in hard copies of anything, come by and visit us. We'll be able to provide you with some more information about the things that I'll be covering today. So here's a brief outline of the talk. Basically, what I'll do is I'm just going to try and step through the title of the presentation. I want to talk a bit about, okay, so what does rapid mean? What am I talking about if I talk about rapid change? Then I'll talk a bit more about Arctic change in general, but as Althea already mentioned, my own research interest is more in the marine and coastal areas, so I'll definitely be giving more airtime to that part of the topic. And then I'll talk about responding to Arctic change. And again, I'm just going to be skimming this topic, but I'll look at a few examples drawn from Alaska that illustrate where we're currently at with the research, but also with the action, if you will, in terms of dealing with the rapidly changing Arctic. And then the last two sort of fairly brief parts of the talk are looking forward to the future and asking this question, well, how do we, how are we going to plan for a potentially very different Arctic in the years down the line? And then I'll just finish with a brief reflection on sort of regional and global action that might be of interest to you. So, okay, what does rapid mean? This is a figure that gives you a good perspective of why the Arctic is important in the context of rapid change. And I do want to spend a bit of time just explaining what you see here, because this summarizes a bunch of research. I mean, in Arctic research, there's been vast improvements in the way we can use satellites or use other types of instruments to learn more about the environment. But there's also been sort of a more quiet revolution in terms of learning from data from the geological history, the geological past of the Arctic. And the bottom panel here is a summary of a global program that looked at the past 2 millennia in terms of how has the climate changed over the past 2,000 years. And you see different areas compared here. So, and what's shown here is the change in the surface temperature, air temperature, in degrees centigrade per decade over those 2,000 years. And 0 is here, this is 0.2, so 2/10 of a degree centigrade, plus and minus. And you have different areas here, like Europe, Asia, South America, sorry, that's cut off a bit, Australasia, the Arctic, and the Antarctic. And if you look at this here, you'll notice that essentially over between, if you compare the changes for the past 2 millennia shown as solid lines here, and the changes between 1851 and 1930, you'll notice that pretty much they're kind of centered roughly around 0. And for all the regions in the Arctic, what's interesting is they have the biggest range in terms of both positive and negative temperature changes. But you know, roughly there's no clear difference here. However, if we now look at the changes, if we compare, so what's shown here is the same time period, 1851 to 1930, versus our observations from observations and modeling results from 1971 to 2020. You'll notice that the Arctic actually starts to stand out already here, with much higher increases in temperature, on average around about 0.5 or half a degree centigrade, roughly 1 degree Fahrenheit per decade. And that's unique across the globe. You see some areas like Europe seems to show sort of a similar trend, but if I show you the next plot here at the bottom, so this is the same panel that you just saw, what's shown here now are projections of the rate of change per decade in the surface air temperature over the time period 1900, 2000, we're roughly here, 2018, and then out towards the end of the century. So these are now so-called Earth system or climate models. But what you'll notice is that, again, now if you compare all the other regions of the globe, the different continents, with the Arctic, we see that the Arctic stands out as a region where we're both seeing and expecting to continue to see the largest changes and rate of change in surface air temperature. And that's remarkable also because we do know from a lot of the evidence that's been coming in over the past 10 years, we have a much better understanding of how rapidly the Arctic has changed over the course of recent geological history, so talking about the last few hundred thousands to few millions of years. And these rates of change over this extended period of time are quite outstanding, very different from what we've seen before. And so that's one of the questions that a lot of researchers grapple with is, what does that actually mean in terms of what we'll see happen in the Arctic? That's something I want to explore a bit more. So if I talk about rapid now, I'm talking about rapid in the context that the Arctic is that part of the globe where we're seeing the fastest changes, where we're expecting to see continued rapid change throughout the course of much of the century, and also rapid in the context that some of these changes, as you'll see in Alaska, where some of the rates of change are even higher, that rapid, very fast change is having big impacts on a range of parts of the environment, animals, wildlife, people, what have you. So if we talk about rapid change, we also have to just sort of put our frame of mind around the timescales that matter here. And so I wanted to share this graphic with you that we'll look at various parts of the talk again. So what's shown here is just a generic timeline going from 0 to 100. So basically you see the sort of a century time scale mapped out here. And I'm comparing now the typical characteristic timescales of different types of natural processes, timescales that are relevant for, so this would be the natural environment. So for example, subseasonal and seasonal timescale, well, that's anything below a year. And then as you go to typical interannual variability, and I'll show you some examples of how much variability we're seeing in the Arctic. That's typically referred to as a timescale of about 1 to 10 years. And then we have this timescale here, sorry, that's out here. Then we have this timescale here between about 10 and 30 years. So by definition, and that's an important point, by definition, climate, if people talk about climate, like a good example is actually, I just heard from Rick Tolman here with the Weather Service that the temperature and weather observations at the ag station out at the, down the road here, that's one of the long, or that is the longest consistently measured location in all of Alaska. It's been around for over 100 years. If you look at that, the classic climatology science basically says that climate is stable on a timescale of 100 years. In fact, climate is stable even on timescales as short as 30 years. So the classic model of climatology assumes that once you measure something like air temperature for 30 years, it varies from year to year, but then it's not going to change anymore. It's just going to be level, right? It's just going to stay the same throughout. It's going to have some interannual variability, but the average is not going to change. And that's an important aspect because if you look at this building even, in Alaska currently, the design of infrastructure, the design of housing, of roads, what have you, is based on the concept that the climate doesn't change. It's, you have interannual variability, it can be large, but on timescales of decades, it basically stays the same. And it's an important aspect that maybe we can talk a bit more about because there's of course, the recognition that this is changing, we have to deal with it, but it's not straightforward of how to deal with that. So I want to point out that in general, if you talk about climate, the timescale of 30 years is important because that, by definition, in the US Weather Service, if they talk about climate data, it's basically the last complete 3 decades, the last complete 30 years. That's what we call climate. But then, of course, you've got a whole bunch of other variability, these so-called multi-decadal cycles. They can play an important role in the Arctic. And superimposed on all of this, we're now seeing rapid climate change. So that's the natural environment. The built environment, I'll talk a bit more about later as well, but again, if you have seasonal operations, sometimes you only operate in the Arctic for part of the year. I'll give you an example of industry, how they do that. So that's a relevant timescale that matters here. If you look at information technology infrastructure, if you look at sort of small scale or transportation infrastructure project, typical timescales, maybe go up to 30 years in terms of lifetime or when you have to start to think about renewing these. And then once you go into community, urban or energy, large-scale resource infrastructure, you're looking at timescales beyond 30 years, in some cases as much as 100. And so these planning horizons are important, and I want to cover that a bit more. And then finally, up here you have sort of socially relevant timescales. You've got our legislative cycle, you have what you might call the business cycle here. I actually had to look this up. I'm not an economist, but apparently if you average it over the past 100 years, the typical business cycle between periods of depressed economic growth and greater economic growth is 5.8 years or something like that. And then, of course, you have the human generation timescale, and you have timescales of political systems, which, of course, can extend out quite a long time period. And what I'd like to do in the course of this talk is just remind you of these different timescales as we look at Arctic change and what are the implications of some of those changes. Okay. The one other thing I'd like to sort of leave with you as a question, maybe something we can talk about later, and that is, if we look at a rapidly changing Arctic, a question a lot of decision makers or planners ask is, are we actually able to respond to the changes that we're seeing effectively at the local, national, circumarctic, or global scale? And you're probably familiar with a lot of examples from Alaska or elsewhere where that is or isn't the case. As a researcher, I myself, but also the Arctic research community in general, is asking a similar, somewhat related question increasingly. and that is whether the research community is actually capable of providing information that is relevant, timely, and accessible, readily accessible, to support those people, communities, organizations, governments, agencies, what have you, that are actually responding to rapid Arctic change. That's an important question. And you know, you be the judge. You know, we'll go through, you know, I'll give you some examples, and then maybe we can chat about that a bit more. Okay, so now let's look at Arctic change. And I'd like to sort of start out at the large scale, but then I want to highlight in particular the Bering Sea here in Alaska, because this past winter there's been some very interesting developments that I'd like to look at in a bit more detail, because I think we can learn a lot about how the Arctic environment is changing by looking at the Bering Sea in a bit more detail. But the first thing is, you know, something that all of us are quite familiar with, and that is that in general, you know, if you just read the news or follow various kinds of national, international affairs, I mean, it's clear that the North is changing, right? I mean, Governor Walker currently is in negotiations with the government of China for a long-term contract to provide liquid natural gas out of Alaska to China, you know, gas from the North Slope. I'm sure that some of you in the audience have heard this 2 or 3 or 4 times over in previous administrations, but clearly that's a key thing. But there is a lot of expansion of global geopolitical and economic interests into the North that I would argue are different from what we've been seeing certainly over the past several decades. And at the same time, we see these large changes in the environment. We have significant changes in northern populations and indigenous cultures, and increasing interdependence between all of these processes. And so as a researcher, I increasingly think of, even though my background is in geophysics or in the geosciences, I increasingly am forced by these developments to think about the Arctic as a social environmental system. What does that mean? Again, we can talk about that a bit more, but you can't take people or ecosystems out of the equation, and that's an important recognition. So if we look at rapid change and we ask ourselves, well, what parts of the Arctic are actually important on a global scale, there's a lot of research over the past 10, 20 years or so that gives us a good idea of what are some of the processes happening in the Arctic that are globally relevant. And this is a map here that just has a few labels on there. And these labels refer to aspects of the Arctic system that have the capability to influence other processes or the global environment at a global scale. So for example, Arctic sea ice cover is a good example. The Arctic sea ice cover is a globally relevant regulator of the climate system. There's the boreal forest here. Again, that's a globally important store and sink of carbon. There are other labels here, like the Greenland ice sheet, very important from the perspective of global sea level. So these different aspects are important aspects of the Arctic. What I find interesting is that if you look at these, all of these are being studied in detail at the edge, at the cutting edge of the field by researchers here at UAF. You might have heard from some of them, but that always motivates me, because I know that if I ever have a question about the boreal forest, I don't even have to go down a set of stairs. All I got to do is walk down the hallway, and there's one of the leading experts on this topic in our building. That to me is just great. I mean, there really is no other place worldwide where you have this density of expertise, and some of the expertise is here in the room. So this gets to the relevance, and I want to focus on a few of these things, including the Arctic sea ice cover. I'll talk a bit about permafrost. I'm not going to cover the boreal forest much, but also talk a bit about sort of the relevance of sea level here. So the first thing to remember or keep in mind is that because of the snow and ice masses that we have in the Arctic, and this would be the sea ice cover, would be the snow cover, would be glaciers and ice sheets, and also the permafrost to some extent, but in particular the ice masses that have a high albedo, that reflect a lot of sunlight. Because of the presence of these bodies of ice, if we look at the trends in the global air temperature for the winter period, November through April, and the summer-fall period, May through October, we find that on a global scale, you see a lot of yellow and red here, some white. So this is the linear trend in temperature change, absolute change over the time period 1961 to 2014 based on observations. But you notice that the Arctic is much redder. And in fact, if you look at the scale here, this scale is much coarser on this end. So in fact, we're finding that the average warming that we're observing over the globe as a whole is amplified by a factor of about 2 to 4 in the Arctic, in particular in the wintertime. And that's an interesting aspect. Somewhat in the summer, but not quite as much, and that's something we can talk a bit more about later. But this aspect of amplified warming in the Arctic is important because that in part also explains why we're seeing such large changes in Alaska. So what do those changes look like? Well, I already mentioned the sea ice cover. This map shows for the time period between 1979, when we have the start of reliable global coverage of satellite data, to the fall of 2017, shows the changes in ice concentration, the amount of ice per surface area per decade in percent. So the scale here goes from reduction by as much as 20% per decade in the negative, and then in the red would be positive. And you'll notice there's just a lot of blue here, and in particular the largest area of blue is north of Alaska and north of eastern Siberia. In this area, we've lost as much as between 15 and 20% of the ice cover, of the summer ice cover, end of summer, September here, over the past 3 to 4 decades. So this really is, the former Coast Guard commandant basically referred to the fact that, well, hey, we just got a whole new ocean out there, right? Because this area was ice covered, pretty much inaccessible other than to heavy-duty icebreakers. Now this is all open water at the end of the season, and that's an important aspect. But the one other thing that I want to highlight, because that gets important now as we delve into this in a bit more detail, if you look here, so this is Bering Strait, St. Lawrence Island, this is the Bering Sea. What's shown here is the same type of measure of the changes in the concentration or the trends in sea ice concentration, but at the time of maximum sea ice extent in March. And you'll notice that over this time period, 1979 to 2017, it's difficult to see, but this actually is mostly red here. The ice has been more extensive. There's been a trend towards increasing sea ice extent in the Bering Sea over the past 4 decades. And so for those of you who've ever watched, The Deadliest Catch, I mean, the fact that you've got more extensive sea ice out there and you have, crab industry fishing boats and others get into trouble, that's exciting. Makes for a lot of good TV coverage. But it's also important to keep this in mind because it doesn't quite jibe with everything else that I've told you about. And in part, that's because this is a fairly small region, and the sea ice cover here in the winter is very much dominated by what the weather systems in the area do. The important thing is, and that's something I want to look at in a bit more detail now, is that trend in the past 2 to 3 years seems to have reversed itself. And so let's look in a bit more detail now at the ice cover of the Bering Sea and what the implications of changes in sea ice here are also for the adjacent parts of the landmass. So here's sort of a brief summary of this past winter, 2017-2018. This just gives you a bit of a flavor of what I want to cover, but the key point is, to take things, or to give you the gist of it, is that this past winter is the record low ice year that we've experienced in the Bering Sea, with substantial implications for coastal communities, walrus, but also maritime activity. And I want to look at that in a bit more detail. So now let's look at this area. Here's Bering Strait. This is a satellite image from mid-April this year. This white stuff here is sort of loosely scattered sea ice. This is St. Lawrence Island. There are some clouds visible here as well, this hazy stuff. But if you ever follow these satellite images, there's a really striking thing that you might notice here, and that is that there is literally no sea ice whatsoever in the western Bering Sea. No sea ice whatsoever. That is extremely unusual. We don't have any reports of that. And it has significant implications because normally this is where walrus like to hang out. And in particular, walrus mothers and their calves spend quite a bit of time here before they, in a typical ice year, would get on a piece of ice and drift northward with the receding ice edge. This year was very different. Also notice, so this is Kotzebue Sound here. No shore-fast ice. Big difference. The Northwest Arctic Borough used to put in an ice road up until a couple of years ago, and people used to run snow machines across here. None of that this year. Very, very unusual. So what's going on? Well, in terms of unusual conditions, again, another few photos. This is a photo Curtis Nakpuk took. This is second half of February, 22nd of February this year. No sea ice whatsoever in front of Shishmaref in the winter. Large waves coming in. If you don't have sea ice, you don't dampen the wind-generated waves on the ocean. So that's a big issue. Here is a photo from Little Diomede by Henry Suluk. Little Diomede, so just to orient yourself, so Little Diomede, I can't really see it, but it's over here in there somewhere. And years past, until about 10 years ago or so, they used to, for several months in the winter, have ice that was firmly attached to land that they would use to land planes on to resupply the community. None of that. This year, they had large waves crashing into shore, doing quite a bit of damage with these ice boulders that were forming in the heavily agitated ocean. So that's very, very unusual. Okay, so what does this have to do with it? I don't know whether anybody's ever seen this type of painting, or any historians in the audience who might recognize what this is. This is well over 100 years ago, painted towards the end of the 19th century. This is a bunch of whaling vessels stuck in the ice at Herschel Island. In those years, the ice never really left the north shore of Alaska during summertime, and in some years, such as this one, you had a bunch of vessels that were stuck in the area, had to overwinter. But again, people were happy playing football and baseball. This is a painting that's in the New Bedford Whaling Museum. Why am I showing you this? Well, John Walsh at IARC, one of my colleagues, generated a sea ice atlas that was based on a bunch of ship logs for all of Alaska's Arctic, going back to about 1850. And from this data, we actually have a very good understanding of how ice conditions have changed over the past 150 years or so. What you see here is the February ice extent, in hundreds of thousands of square miles. You can see some, there's these cycles in here. In particular, notice that, there definitely was even more wintertime ice extent in the 1960s and 70s. There was a bit of a drop, and then, I mentioned already, there was a slight trend, towards increase. The previous record low was in 2001. This is 2018. So you notice these 2 years really stand out. And the question is, why is that? What's responsible for these low ice extent years? I want to use the previous year, where we already have very good data that's been analyzed, to show you what's been happening in the area. So here's an analysis of the winter 2016-2017, where we've had somewhat lower ice extent, not quite as much, but in those cases, and again, this is a study by John Walsh and a bunch of other people here from the university and the Weather Service, one of the key factors in the area has been that over the course of the winter, both in the Gulf of Alaska, so here's Alaska, there's St. Lawrence Island, Kodiak Island here, southeast Alaska. This shows the anomaly, the deviation from the normal of the uppermost ocean. So it gives you a picture of ocean heat content. And these large differences above normal in ocean heat content are very unusual. This goes up to as much as 1 degree centigrade, 2 degrees Fahrenheit, very, very rare. So some of you might have heard about this. It was referred to as the blob, you know, the warm blob. This heat has been building up as a result of a very strong El Nino. We've entered into what's known as a positive. So if you look at, let's look at the ocean heat content here for the period 1980 through 2017. We've entered into what's known as a positive Pacific decadal oscillation. You can see there's periods where there's much less heat in the ocean in the Bering Sea. There's periods where there's much more. And this interannual variability, but also these extended periods of time play an important role. And they're related to some extent to atmospheric circulation and ocean circulation in the North Pacific. We've now entered into a positive PDO. But on top of that, the analysis by John Walsh has also shown that there's a number of other factors, including anthropogenic climate warming, that's responsible for these heat anomalies. But it's in particular this large amount of heat that gets transported by the prevailing ocean circulation into the Bering Sea and then the Chukchi Sea that explains why we've been seeing such low ice in this region. Why is that important? Well, it's important because, as I mentioned, if you recall, this is the reduction in ice extent between 1979 and 2017 in the summertime. While all of this has been happening, we've actually had a period where the Bering Sea has been putting a damper on that warming. The Bering Sea has actually made the warming we've observed here somewhat less because the sea ice cover has been more extensive. So it reflects more of the sunlight. It helps cool the area. What we don't know is, and that'll be interesting to watch over the next few years, whether the changes we're seeing with much more heat in this area, whether we will expect to see much bigger changes in sea ice over this area in the coming years. So that's an open question, open research question. Well, what are some of the implications of this? I just want to highlight a couple of things here. Here's a study by Peter Bieniek and others. So he looked at the trends in rain on snow events. And those are important because they're important in Fairbanks, of course, everybody knows, you know, you don't want to, there's been days where I don't even want to get on the road, you know, let alone think about driving from one place to another. If you look at interior Alaska, both observations, so anything that's yellow or red, increase in the number of rain on snow events here for the period 79 to 2013. And then here are model projections over the course of the century by two different models. You see a lot of red and yellow here. So we've been seeing an increase. That's going to increase further. You'll notice here, for some reason, there's a decrease in the number of rain on snow events in southwestern Alaska. That's not because there's less rain. It's just because the snow cover is now decreasing so much. Even here, the length of the snow season is so short now that a lot of the rain just falls straight on the tundra. And that actually does have implications as well. So if you look at, actually let me just show you this. If you look at satellite data, this is work by Uma Bhatt and others. Uma and her colleagues have looked at by how much is the greenness of the Arctic changing. This is over the period from 1982 to 2017. So this, I just got this plot this morning from Uma. So what you'll notice is that, and this actually is Arctic-wide, but she's only showing those changes that are significant, and those are confined to the coastal areas. In particular here on the north slope of Alaska, you have much greener vegetation. That's due to growth in shrubs, a less extensive snow cover, but then also kind of difficult to see in the Yukon-Kuskokwim Delta. There's a negative trend, less greenness, and that in some ways is already explained in part by changes in the rain and moisture regimes in these areas. So, but all of these are driven by the changes in the sea ice cover. That's an important thing. So the sea ice cover is directly responsible for a lot of the changes in coastal vegetation. Okay, so now looking at the clock here, Let's briefly look at, okay, so we have these changes responding to change. So what's responding to change? Well, here's one response. Here's 35,000 walrus responding to Arctic change. So this is a Alaska Public Radio headline from actually a couple of years ago, or almost 2015. So what you see here is a massive amount of walrus that are hauling out on land at Point Lay in northern Alaska. These types of haul-out events have been increasingly common. They're a result of the fact that typically walrus in the summertime, as I'm told, and as I've seen it myself, but like to spend time with their calves, resting on ice floes, diving off the ice floe, feeding in the shallow waters of the Arctic coastal ocean. So they mostly feed on clams and other seafloor organisms. But in recent years, the ice has retreated so far, so fast, that the walrus now have to actually haul out on land to rest. And Point Lay seems to be seeing the brunt of this in the Chukchi Sea. That's a big change. And these walrus, it's interesting because, I always thought, well, a walrus, okay, so what, whatever. But as I've learned, walrus they get old, they're very intelligent, and they actually seem to make decisions, or in particular the older females seem to make decisions that, no, we're not going to waste our time moving back and forth here between different points in the ocean. We're going to go on land and rest. So these walrus actually are in some way already responding at some level to Arctic change. Well, there's other responses. Here's how the maritime sector responds. If you can make money by saving on fuel or going on a route that previously was inaccessible, you bet there's some shipper somewhere in Malaysia or Singapore or China or wherever that is going to pursue that option. And so we've seen a substantial increase in the ship traffic through Bering Strait here from the 1990s into, this goes till 2013, 2014. In the more recent years, this has increased further. Some of you might have read just this past winter, there was the first transshipment of Western Siberian gas from the Western Siberian gas fields through Bering Strait in the winter in a vessel that's jointly operated by a Japanese and Russian company. So increasingly we're seeing vessel traffic in the Arctic, in part also driven by environmental changes, but of course also driven by global processes. And then, here's another type of response I briefly wanted to share. This is a group of Inupiaq hunters from Wales. Out on the sea ice, they a lot of coastal communities, in particular on St. Lawrence Island, Bering Straits area, a lot of their protein, a lot of their fat comes from marine mammals, in particular walrus. You see a walrus resting on ice here. The Inupiaq and the Yupik like to hunt walrus on sea ice because it's easy to butcher. You've got room, you can really get into it and do a clean job. But that's been getting more and more difficult. Here's an example of a study a graduate student working with me a few years back, Marie Kopsch, did. What this shows is for the community of whales here in Bering Strait and the community of Gamble, the ice concentration over the course of the year. So this is a lot of ice, around 80% or so in the vicinity of St. Lawrence Island. Up here, whales, even more higher ice concentrations going up to 100%. And you'll notice that if the ice concentrations are this high over the course of the winter, so this is freeze up here in around October or so, and then break up in around May, June, during the winter, really there's no boats that are venturing out from whales to hunt walrus or other marine mammals. In Gamble, in the mid-2000s, the community completely switched how they hunt marine mammals. And you'll notice that this year, where we had very good records, local observers, Leonard Apungaluk among them, we have good information that hunters were out all winter long because at these concentrations of ice, you can actually already get a boat out. And this year, if I would have, actually now looking at it, I should have done it or I need to do it. If you replot this for this year, you would be at 0 all winter long. There was no ice at Gamble for the entirety of the winter. And so one big question is, what are the walrus doing? And B, clearly this year, I mean, the past few years, 2008, so this is 2008, the then governor of Alaska already declared a disaster for St. Lawrence Island because the communities were not able to harvest enough walrus. This year, I would be surprised if that's not going to happen again. So that's a response at the local level. So now here is, sort of thinking about responses. You can respond. I mean, local communities, hunting crews like this are extremely good at responding. They know the environment. They follow everything on a daily basis. There's this expression. Some of you might know a book by Jim Barker, local photographer, always getting ready. There's this idea that in a lot of Yupik and Nupik communities, people are always ready. I mean, they follow the environment very closely. These communities are great at responding to change, probably better than any other community or organization that I'm aware of. As a scientist, of course, I'm sort of asking myself and a bunch of colleagues, well, okay, so responding to change, what does that actually mean? What you see here is, and I'm not going to go into all the details, but this is the outcome of a 2-day workshop of a bunch of researchers from the social scientists, biologists, engineers, physical scientists, kind of wrapping our heads around, okay, what does responding to change mean? Responding to change, it should be precautionary, proactive, iterative. There's a bunch of interesting words in here. You're essentially responding to variability and complex changes in the Arctic system. And who's responding? Well, it's what social scientists refer to as actors and stakeholders. So this could be people, organizations, governments, what have you, at different scales. What I'm interested in is, and a lot of us at IARC are interested in, is what type of tools in terms of data products, information, scenarios, options, do we need to be thinking about and working on to provide to decision makers so that people can actually respond more effectively? And so I want to just spend the rest of the talk here quickly reviewing and giving you some examples of these types of tools. And for this, again, the time scale is important. The first example I'll share with you is on a seasonal time scale. It's based on a collaborative effort in the Bering and Chukchi Sea area, the so-called regional sea ice outlook, or sea ice for walrus outlook. So this is a collaboration between the National Weather Service, the Eskimo Walrus Commission, which is responsible with the federal government to manage the walrus populations, the University of Alaska, IARC here in town, and a large number of hunters and communities who are basically helping validate and improve weather forecasts and ice forecasts for the region. It's a great example of a group of people getting together and collaborating informally initially, and now somewhat more formally, and using everything that's at our disposal to improve safety of people who are out on the ice or at sea. So as an example, it includes satellite images here. Here's an image of the shoreline between Wales and Shishmaref. You can see these pieces of ice breaking off. Those are significant hazards. But it also includes, very importantly, observations. Here's an observation by Curtis Nerkbuck from Shishmaref, who reported about the state of the sea ice cover. This is a photo he took. You can see a couple of hunters from Shishmaref driving across this type of ice, flooded here, and anomalously early flooding of the shore-fast ice here, to access the edge of the shore-fast ice where they put the boats in to pursue marine mammals offshore. But what's interesting is, in particular, Curtis and Ayakpuk, but also others, are very sophisticated, and in some respects, Curtis is much more knowledgeable about information sources than I am. We've worked with him and others in the area, and actually were able to get some support from the Japanese Space Agency, JAXA, who's been launching a satellite, and you see a satellite image here. I'm not going to go into the details, but this type of satellite information actually makes operations at the local level, including safety of hunters, improves safety of hunters and the safety of local operations. So both industry and hunters are using this information, and this effort here is a way to jointly explore that. So that's a time scale seasonal. Let's look at an example on the time scale of about 1 to 30 years, almost going into the longer kind of large scale infrastructure time scale, and that is the flooding of the Dalton Highway in May of 2015. Some of you may be aware of this. What you see here is a Landsat image. Up here is kind of difficult to see. This is all the Pearl Bay infrastructure. Let me blow this up a bit. So this is the center part here, or no, sorry, here of the image. And what you see here, you see these lines. This is actually TAPS. This is the Trans-Alaska Pipeline System. The road is on the right here. This was all flooded. Traffic was shut down. The state, Alaska Department of Transportation, had to respond immediately. There was a bunch of trucks stuck on the road because of this flooding. Was this flooding foreseeable? No. This actually hadn't happened both in terms of satellite records, longer-term weather records before. This was a result of an extreme melt event. And these types of extreme melt events are now increasingly common, resulted in flooding where the water couldn't run off. The Dalton was not designed to deal with that type of challenge. Alaska Department of Transportation had to put in just $70 million just to get things fixed so that you could reestablish traffic. And they're now working on a project on the order of about $100 million to kind of proof this last stretch of the Dalton to avoid these types of problems in the future. So this is maybe 40, 50 miles of highway. It gives you an idea of the costs involved in responding to a changing environment. Here's a photo, yeah, so this is what it looked like here, right? And you can see a highway washed out. Important to note also, wasn't covered in the media, community of Nuiqsut, they actually had their freshwater lake breached by these waters and were running out of potable water because this is very, very sediment rich, not good stuff to drink. So that was another big issue. And since the North Slope Borough, working with Arctic Slope Regional Corporation, actually has tried to see what do we have to do with our water supply systems at the local community level if we see more of these rapid thaw events in the future. What we're doing here at the university is, and I'd like to highlight this is part of the PhD thesis of Rick Lader, who just successfully defended his PhD a couple of months ago. So he's been working with the Alaska Department of Transportation where they told him, look, I mean, for the work that we do in terms of road infrastructure design, there's certain things we need to know about how much rain falls in extreme rain events. You know, what's the frequency, for example, of rain, rain on snow events? And so Rick has looked at a range of things. You know, and I'm just again, don't focus on details. I just want to highlight sort of the types of products he's generating. So he, for example, has looked at, okay, if we have fewer days below freezing, what does that mean? He's looked at, and of course that isn't necessarily always bad, right? I mean, people know Fairbanks, we're increasingly getting favorable growth seasons. So Rick also, as part of his PhD, has looked at increases in the length of the growing season and increases in longer working seasons for the industry in interior Alaska. But he's also looked at increasing heavy precipitation events and the flood risk that comes with this. The key point is that currently the state of Alaska, both in terms of the state itself for its own operations, but also engineering companies and others, do not have yet this type of updated information. They're relying on a sort of environmental engineering atlas that was put together in the 1970s and 80s, hasn't been updated. So a lot of the design up until, in particular, the group under Scott Rupp at IARC, the SNAP group started putting out these products, was relying on a paper atlas that was put together in the 1970s and 80s under the concept that climate doesn't change. You know, it varies from year to year, but it's stable. That is the biggest issue for the state of Alaska, is the fact that, and anybody operating here, including industry, you hear a lot about increased pressure for development on the North Slope. I mean, ConocoPhillips is investing heavily, so are others. Industry itself now has new codes that require them. And these are self-imposed codes. These are not government-driven codes. These are codes where industry says, hey, we're going to get together under the ISO, International Standardization Organization, and we're going to figure out how we can be better in terms of planning long-term infrastructure. As part of that, they actually need this type of information but have difficulty getting it. So that's one of the areas where there's a lot of room and opportunity for improvement. All right, so I went a bit longer, but you know, Althea, your introduction was like 20 minutes, right? So I've got another little bit, but now just briefly, I just want to do two things. So the first thing is, okay, so this is all going on as we speak. How do we plan for the future? The big challenge is this time scale here, right? Because what I've shown you so far really was focused mostly on what are we observing, you know, what do we know is happening. Now we're asking, you know, if you think about new communities, community relocation, or a lot of the infrastructure projects that are being discussed for the North Slope now, these are at the very least 30-year lifetimes that these pieces of equipment or whatever it is, the built environment has to last for. How do you plan for that? And that's an area where the types of products that the example I showed you from Rick Lader's thesis are useful, but they're not sufficient. There's still significant uncertainty associated with some of this. That's a big challenge. One of the things that we've explored is to develop scenarios jointly with the stakeholders or the people who actually have a say or an interest in this information. And in the interest of time, I'm just going to quickly jump through this. I'm just going to show you a couple of very coarse maps. This is something that was produced under the North Slope Science Initiative. Never mind the labels, and actually this didn't reproduce well. But a couple of years ago, 2016, we, a group here at UAF, led an effort to help industry, local government, tribal organizations, and others sort of figure out what are scenarios for oil and gas and energy development on the North Slope. And this was in the waning days of, so it was 2015 was the key workshop, when Shell was still operating in the offshore. Everybody, you know, the scenario was, oh, we're going to have all these pipelines running out from the Chukchi Sea, and there's all this development. And you had to force people to say, no, that's one plausible future, or one option, but maybe none of this is going to come to pass, and the North Slope might actually revert with a decline in infrastructure, where the big challenge is how do you clean up the place? So this group of experts, around 60 or so, developed different scenarios, identifying drivers like the price of oil and gas, biophysical drivers like climate change, extent of sea ice. And what's interesting is initially there was a lot of skepticism that this really is useful, you know, because it's sort of expert opinion. There was a lot of internal discussion. But if you follow the news, you might have heard about the A-STAR project. It's a project that was initiated by the governor and the mayor of the North Slope Borough, Harry Brower Jr., basically putting in place low-maintenance roads that link North Slope communities, jumping off of oil and gas infrastructure. And that group actually found these scenarios that this group of experts developed to be quite useful. So this is a serendipitous outcome, wasn't really planned, but it's a good example of why drawing on scientific information, going through this process and generating data products is actually useful. Here's another example that was led by Amy Lovecraft here, looking at community health and sustainability jointly with the North Slope and the Northwest Arctic Borough. And again, I'm going to jump through this here in the interest of time. So I just want to end with 3 slides here. And they essentially summarize kind of where are we at now? What is it that, you know, is exciting, but also what is it, if we think about responding, you know, it's about action at the regional and global level. What type of action can we take? Well, there's a whole bunch of options. But the key point is that increasingly there's a recognition, both within the state, nationally, and globally, that the Arctic provides important services for all of humanity. That's like a pretty highfalutin statement, you know, but if you actually look at the numbers, and there's research demonstrating this, for example, the Arctic sea ice cover is the key climate regulator on timescales of about 3 to 4 decades over the past 3 to 4 decades. Ice sheets, key aspect in sea level regulation. Then, of course, you've got marine food webs. You have the importance of the Arctic as a place where tourists might want to go, or where indigenous peoples identify with their cultural landscape and their home. So this recognition, then I actually tend to think, I tend to be a kvetching optimist, I guess is sort of what I would characterize myself. It's easy to complain, but ultimately, I actually think the Arctic is calling the global community to action. In what ways? I'd just like to highlight two things. The current administration, Alaska administration, has a draft Alaska climate change policy. All of you here can go to this website, read the document, it's not very long, and comment. Nils Andreasen, formerly with the Institute of the North, is actually compiling all this input. And if you look at the sort of the 5 goals, these are actually tractable. Some of them are pretty far out there, but there's steps that we can take to address key issues. And so I'd encourage you to look at this. But, I alluded to this earlier, the governor has been in conversations with Xi Jinping, president of China. I just got back from what we call the Arctic Observing Summit 2018. In 2016, UAF hosted the Arctic Observing Summit, Arctic Science Summit Week. We had over 1,000 researchers, government officials, and others here, high level. We just had the follow-on meeting, 2018, in Davos, Switzerland, with representatives from, I think, 28 countries. And what this is this really was remarkable. I'm excited about it, and in part I derive my optimism from these types of meetings, because we had indigenous people representing indigenous governments and organizations, industry, a lot of government agencies from a bunch of different countries, recognizing that if we want to work with a changing Arctic, we have to know what's happening, and that requires observations. And what has me optimistic as well is the fact that recognition has led to what's known as the Arctic Science Ministerial Meeting, where you have ministers from all these nations here, and these include nations like Singapore, Russia, USA, all the Arctic nations, but also countries like China, Japan, and others meet to identify what are the key issues that we need to tackle, and how do we do that outside of the fairly slowly grinding mills of standard diplomacy. So the Arctic Observing Summit that we just wrapped up is actually providing direct input to the Science Ministerial, and that's where, again, if you look at the different organizations, including indigenous peoples groups that are part of this, tells me that this recognition that the Arctic is important will lead to action. It's up to us to move that forward. Thank you. So do we have time for questions?
We've got time for questions, and if you could repeat the question, that way.
Yes, yeah. And if you want to leave, if you have to leave, just leave. Don't worry, don't feel this is impolite or whatever. Yes, we've got one at the back.
I looked at temperature data for Boulder, Colorado, and Fairbanks for the last 80 years or so. Now in Boulder, the temperature had gotten gradually warm over the past 80 years using a linear curve fit, but that was more because there were fewer colder days rather than more warmer days. On Fairbanks, same thing, said fewer colder days, less than -40 now than 80 years ago. So is this some kind of a general trend worldwide? Because I hear all the news about all these heat waves we're having around the world in the summertime.
Okay, so great question. Question is, looked at temperature data for Boulder for the past 80 years in Fairbanks. Boulder, fewer colder days with an upward trend. Fairbanks, similar. That's a good point. The one thing I want to be clear about is Fairbanks and Boulder, those are fairly small areas, right? I mean, you cannot look at individual stations and say, okay, here's the global trend. That's one of the challenges that, even I tend to fall into this trap where I go, oh, the past few years have been warmer. I mean, the area that determines the climate in Fairbanks or the processes are such that even Alaska as a state is sort of just bordering on the size of the area that you have to consider as a whole to look at meaningful trends in the climate system. Now, what you're saying, though, in general is true, that both in Alaska we have fewer like the number of heating degree days. You know, the days, sort of the degree of coldness in the winter here has been dropping, you know, which of course a lot of us appreciate. And that's true in many other places in the Arctic. At the same time, though, if you think about Alaska, the biggest changes we've seen in Alaska are along the coastal regions, in particular in the Arctic, and those are more connected, as I explained earlier, to the changes in sea ice. And those changes in sea ice, like the sort of the area over which sea ice is influenced is much larger. It's actually a better indicator of climate change, if you will. So in that context, I wouldn't want to say, oh yeah, Fairbanks has seen this type of weather more recently or whatever. That, in the big picture, is not as significant. Now, but to get to another aspect of your point, a few years ago, I was part of a project where we, a group of us, of experts working in different areas of the globe, tried to identify areas where we feel there is the scientific basis is compelling to allow dividing out the human cost component of climate change from natural variability or natural changes. And so we did a broader survey, and the three regions where, so this was in about 2014, the work was published in 2015, that's changed since, but back in those days, the three regions where there was very solid evidence were Alaska, along the lines of what I explained, the Andes, where you see significant changes in mountain glaciers, mountain permafrost, and impacts. And the third region was Australia. So Australia is large enough, and there, in fact, what's happened is that they have seen a significant increase in the number of dry, hot days, and the impacts there were mostly large wildfires. And if you followed the news, I mean, Australia probably globally is the country that has the biggest challenge in terms of urban-wild interface, large damage and decrease in the quality of life in people who are living in areas where you have major wildfires now in the summers. Yes?
Could you go back one slide to the Arctic Observing Summit there?
Yes.
Because that seems like a very important type of forum that will take a long time to for these various groups to reach agreements, because they have different directives here.
Yes, okay, so I don't know whether everybody heard it, you know, Arctic Observing Summit. I sort of hear you're saying, well, it'll take a long time. It's a challenge to get these groups to reach agreement on what to observe, how to observe this. And I agree with you fully. But what is amazing, and that, you know, I mean, this was the fourth observing summit. The first one was all over the place, 2013, you know. The second one was a bit less all over the place, but it went in the wrong direction. The third one that we had here, I like to think we actually got sort of people on the same page. This one now, you see suddenly there's a process, you know, there's enough momentum built that there's consensus starting to emerge. And to me, that is one of the most powerful ways in which we as researchers can help not necessarily drive change, but support those governments, individuals, you know, communities who want to respond to change. To give you an example, so exactly that type of problem, Sandy Starkweather, who is the lead of the US Arctic Observing Network, she works for NOAA, is a federal employee, oversees and coordinates all of US Arctic observing activities, and myself more as a, you know, offshoot academic. We were chairing a working group that was actually getting at this question. How can you take the pieces that already exist and just get people to recognize, look, don't just measure your favorite parameter or whatever, you know, do it in such a way that you can build something out of these pieces without having a central government or some entity come in and say, okay, here's how everybody's going to do it. You know, how do you grow a network like that? And what was amazing to see was that we had about a dozen people on our working group. You know, we had these calls where we covered all the time zones in the world. You know, we had people from China, Japan, Korea, Europe, a couple of indigenous organizations representatives, and it took us several months prior to the summit to kind of get an idea of, okay, what, how can this be done? And I think we've figured out a path how to do it. And I'd bore you to death if I were to tell you, but I'd be happy to chat with you afterwards. And then you take that, so you have about a dozen people who agree on this internationally. And these are people, these are higher level people, people who sort of can sway opinion or direct programs. We walk into the summit where you have now you're talking like a couple of hundred people or more, but you sort of present this vision and you start to see over the course of about 3 days all of this congeal. So now all of us are working on, okay, now we have to get into the science ministerial, because that's where you have countries with real financial resources and the will to do something that are just waiting to pick something up that to them is tractable, where the minister and the agencies under the minister level know that the group that's coming to them has done their due diligence, which is important, and something that generates benefits, both societal benefits, economic benefits, what have you. And it's interesting, I'm not saying that we know what we're doing or that this is actually going to succeed, but over the past several years, there's been a lot of efforts to sort of link all of these different aspects of the problem. So, but you zeroed in on that's the big problem. It really is. All right. Yes.
Somewhat of direct follow-on to that, it has been scary and worrisome that the state of Alaska has some fiscal problems, and if they're going to disassemble the university, we're going to give away something that can't be recreated. I'm heartened to hear you say that potentially, internationally, they can help carry us, and that you're doing, and that IARC and our folks are important enough that they'll be retained. That's my question.
Yeah, that was a softball. Again, I don't know whether I have to repeat it, but let's just do it, because I thought you put it very well. State of Alaska discussing fate of the university because of a lack of revenues. How can we maintain the expertise we have? And if you go into the ranks of researchers, faculty members here, the past few years have been very difficult. As you know, we've lost a lot of people. A lot of people have been lost through attrition because they just felt, I cannot do this anymore. The institute I've had 3 people leave. We've had to let people go or not renew positions, but I can tell you that I've had 3 people leave who were just doing excellent work, absolutely excellent work. They could have weathered all of this, but it's just that if you of course we try to work around these issues, but at the same time, if there's alternatives, right? People take them. And so 2 of them now work for federal agencies, one for the Naval Research Lab and another one for the River Forecasting Center in the state. And both are doing fantastic work. A third person went to a different country. So there is that risk of losing the expertise. But at the same time, I feel, in particular, this session was, legislative session was, you could see, okay, people are starting to think about this stuff. And at the same time, I also feel that these are tough times, but the university is great because people are pulling together, and we understand that's part of the process, right? Ultimately, if the university is not able to demonstrate to the state, the people of Alaska and the legislature, that we are of value, and we haven't done a good job in the past, then that's a challenge. On top of that, I would say, that these international connections are helpful because we have people come here to learn about what we're doing. Last year, for example, we hosted a high-level delegation from China, Chinese Academy of Sciences, that included the former head of the Chinese Meteorological Service, which in China is at the level of a cabinet a minister. These are very powerful people. the Chinese Academy of Sciences is a very impressive body, intellectually and the resources they command. But what was fascinating to me was, so we took them out to Nome and Kotzebue, both communities, you know, the university has campuses there, they met with local native leaders. There was a really interesting discourse between different groups in those communities about what you know, because I mean, let's be blunt. I mean, if a group of Chinese comes into Nome or into Kotzebue, the first question is, well, what are you here for? You know, are you trying to build a port, or are you trying to do whatever? You know, but after spending 2 days in each of those communities, suddenly you start to see, no, there's actual communication about the same types of issues. Chinese researchers, and in particular at the Academy of Sciences level, they have bought into these broader international collaborative programs, and that also allows us to weather some of the challenges we find here. So, an important aspect of Arctic research. Thanks. All right. Yeah, we've gone for a while, so thanks.